Hello students, welcome back. Now let's go to the second half of section 4, and that's where we're going to consider these kind of asymptotes. Slanted asymptotes, or if time permitting, curved asymptotes. Okay, sometimes horizontal asymptotes are not enough for the end behavior. And that happens when the degree of the numerator is 1 larger than the degree of the denominator. In that case, you do the polynomial division, numerator divided by the denominator, and get the quotient. And this quotient polynomial is going to be the asymptote, because this remainder has degrees strictly less than that of the denominator, so this fraction will go down to 0. So when x is large, this part just drops out, more or less, and this quotient polynomial and this rational function will behave pretty much the same way. Now, the difference of degree is 1, then this quotient has degree 1, so we have a line. Here's an example problem. So we have previous example problem here, 2x cubed plus x to the negative second power minus 1, like that. Okay, all right. How do we work it out? Here's a solution. Multiply by x to the second power to both numerator and denominator and simplify. You get this expression. That's something we did before. And then from here, we do the polynomial division, and if you do it right, then you're going to get this quotient, and then the remainder over the denominator. How do you get this polynomial division done? Too time consuming, so I'm going to just leave it at that. Especially considering that we have these fractions, I don't want to do this. We end up with something like this. So this one is just small scale, -3 to +4. Here, -10 to +10. Here, you can clearly see the asymptotic behavior. That's how you get slanted asymptote. Some people call it tilted asymptote or oblique asymptote. They mean the same thing. I'll usually use the term slanted. Our textbook uses oblique asymptote. I hate that term because other than this textbook example, I never use the term oblique anywhere. Now, before going over to example problems, let me show you one more picture here. If the degree of the numerator is more than 1 higher than the degree of the denominator, then you're going to get curved asymptote. So degree difference is 2 or higher. The same deal. Theoretically, it's the same thing. We do the polynomial division, and the remainder over the denominator, this is going down to 0, because when x is going to become humongous, the numerator has this numerator of this fraction, the remainder, has degree strictly less than the degree of the denominator, so this one goes down to 0. So this original fraction, original rational function, and the quotient polynomial will have to behave pretty much the same way. And here's a picture. So we have something like this, and then what do? You use appropriate polynomial division. And then if you do it right, you're going to get this quotient, and then remainder over that denominator. And if you plot it, this one here is y equals to 2x squared minus 5x minus 11. That's the red graph here, that part. Maybe I should have used red here as well. And blue is the original rational function. You can see the asymptotic behavior. So basically the same thing, polynomial division. However, I'm not going to write this kind of problem in the exam. It's getting a bit too much. It's sufficient for in class, especially showing you some pictures. That's sufficient. Okay, all right. Let's go over to slanted asymptote problems. And the final one here is going to be curved asymptote. I'm going to skip that. All right, here. Slanted asymptote. How can you tell this is slanted asymptote? The numerator has degree 2. The denominator has degree 1. The difference is 1. So if we take the quotient will have degree 1. So how do you do that? Okay. Step 1, the usual, y-intercept, plug in x equal to 0. Horizontal asymptote, no horizontal asymptote. Step 2, factor the numerator and factor the denominator. Denominator is already in factored form, already simple form, so no problem there. And you're going to get zeros from the numerator and pulled from the denominator. So the zeros are going to be x-intercept, and the vertical asymptote will be this pole down here. If you graph it, you're going to get something like this here, one pole, vertical asymptote x equal to negative 1, and then two zeros here, x equals to negative 2 and x equals to 4 here. But then again, what about the slanted asymptote? We get it by polynomial division. I can use long division, but I'll leave the long division process to you. I took a bit of a shortcut here, and let me tell you about shortcut because this is going to be a little less time consuming. So let me expand the font a little bit. All right. From first two, rewrite it into x times x plus 1, so x squared plus x. So this is basically x times x plus 1. Let me highlight it in blue so that you can see that that part and this part is the same. And then I got x squared plus x, so this negative 2x now became negative 3, so that 1 minus 3 is negative 2. And then let's work this one out. I want negative 3x minus 3, so that that part can be written like this. This one we did before. And then the remainder, negative 5, is there. So factoring x plus 1 out, canceling, we just get x. And then factoring this x plus 1 out, that one out, and we just get negative 3. See the color coding, how things are working? You can use long division if you want to, and you can use synthetic division if you want to as well, but I usually find it a little easier and less time consuming to do it this way, as a matter of fact. Kind of like completing the square, to tell the truth. So slanted asymptote is y equals to x minus 3. Enough time for another problem? I guess so. All right, let's go to this one then. The third problem I'm going to skip because that's going to give you a curved asymptote. Now this one, you're going to get a slanted asymptote because the numerator has degree 3, the denominator has degree 2. Now, the synthetic division will not work because we have quadratic down here. So you have to use either long division or the kind of technique I showed you before. As for step 1, getting y-intercept, plugging x equal to 0, oh, that was easy. Horizontal asymptote, no horizontal asymptote, that too was easy. Now for vertical asymptotes and x-intercepts, factor the numerator, factor the denominator, and then you get 3 zeros. X equal to 0, x equal to negative 2/3, x equals to 1, they all have multiplicity 1. And we have two poles, negative 2 and positive 2. If you graph it, yes, we have two poles at x equal to negative 2 and positive 2. And then we have, let's see, 3 zeros Oh boy, they're all here. It's really hard to see. Okay, let me just copy and paste. Oh, excuse me, I have a zoomed picture right over here. Okay, all right. That part over here zoomed in, so we have these three. Negative 2/3, 0, and 1. Okay, I didn't have to use another code there. So that's the graph, but one thing remains is the slanted asymptote. How do you get that? We use polynomial division. Okay, you can use long division if you want to, but I'd like to save some time, so let's do it this way. Let's see. I want x squared minus 4, so 3x cubed. All right, 3x cubed minus 12x. That's gonna give me x squared times x squared minus 4. This one. See the connection there? I want x squared minus 4 as a factor, so artificially make it into negative 12x. Because I made this negative 12x, and then eventually I have to get down to negative 2x, I need this plus 10x. Okay, first step is done. Now let's go to the next term here. Negative x squared. From here, I would like to get this x squared times some factor of x squared minus 4. By the way, this one is already set, blue. And then x squared, negative x squared plus 4 here. So that negative of x squared minus 4. Because I added 4 here, I have to subtract 4 there. And then that's it. We have just first degree polynomial here, that's the remainder. So what's left here is, after canceling this one out after factoring, we have 3x, that's blue. And then after canceling this one out after factoring, I get negative 1, so that's red. So there goes my quotient function. That's the slanted asymptote. And what's left here, well, that's going to be just remainder, so you don't really have to worry too much about it. So the slanted asymptote is 3x minus 1, and that's what we have over here. Okay, as for polynomial division, I'll leave to individual students' method. Long division is okay. It's time-consuming, the most time-consuming process, but it works. And synthetic division will not work in general, so I don't really emphasize that. But the method I just showed you, to me, that's the most effective and the quickest. I have a little bit of time left, so let me show you part C, curved asymptote problem. Denominator has degree 2, numerator has degree 4, the difference is 2. So the quotient function has degree 2, so you're going to get a parabolic asymptote. Like this. And then how do you get that? Well, that's going to be coming from the division algorithm here. Oh, too complicated for my taste. So let's do it this way. Polynomial quotient, and that's the numerator, and then divided by the denominator. And then I have to specify x, and that's my quotient function, 2x squared minus 4x minus 6. That's it. Maybe it's a good idea to remember this mathematical command so that you can use for Wolfram Alpha or something like that. Okay, that's enough for me as far as curved asymptote is concerned. I'm not going to write any exam problem here, but it's a nice thing to know, so I just mentioned it in class time. That's about it.